Hello everyone, welcome to the chemistry channel. So today we are going to be discussing our last topic associated with atomic structure, and it's going to be focusing on electron configurations and how to write them. So with that, let's begin. So an electron configuration is basically a way in which electrons are organized into the different orbitals. So it's basically a bookkeeping tool that we can use in order to organize where particular electrons are in an atom. It allows us to designate the specific orbitals and subshells that the electrons can occupy themselves in. So there are certain rules for writing these electron configurations, and the first rule, and probably the most important one, is the Aufbau Principle. Now, Aufbau is a German word for building up, so it is also called the building up principle. So the Aufbau Principle states that in the ground state, so remember, the ground state means the lowest energy state. In the ground state, electrons fill lower energy subshells before higher energy subshells. So the Aufbau principle states that in the ground state, electrons fill lower energy subshells before higher energy subshells. So you may recall this diagram from our one of our last lectures, and this diagram basically shows you the energies associated with each subshell in a multi-electron atom. You'll see here that the lowest energy orbital is the 1s orbital. The second lowest energy subshell is the 2s, then 2p, 3s, 3p, 4s, and so forth. So you would start filling out the subshells with the 1s orbital, then you would proceed to the 2s, then the 2p subshell, and so forth. So you fill the lower energy orbitals before you fill the higher energy orbitals. So fill the lower energy subshells first, and then the higher energy subshells later for ground state atoms. Now you can sort of visualize this with this diagram here, and this diagram basically shows a general rule of thumb called Madelung's rule. Now, Madelung's rule is just a little rule that you can use in order to help yourself figure out which orbitals are filled first. So the basic idea of Madelung's rule, so let's write it up here, Madelung's rule, basically states that electrons, sorry about that, let's get rid of that. So electrons fill subshells with lower n plus L values first. So it's a general rule of thumb that basically states that electrons fill subshells with lower n plus L values first. And remember that the value n is the principal quantum number and L is the angular quantum number. So here is a little chart showing this rule, and you've probably seen this either in your textbooks or your classes, and it's basically a little picture that can help you fill out the specific orbitals. So if you have a particular electron configuration, you'd start with the 1s orbital, of course, because the 1s orbital is the lowest energy subshell and orbital in the multi-electron atom. So we'll put a little arrow here. And then after the 1s subshell, you'd start filling the 2s subshell. So we put an arrow here. And then after you fill up the 2s subshell, you move on to the 2p subshell. And then after the 2p subshell is filled, you move on to the 3s subshell. So then after the 3s subshell is filled up, you start filling up the 3p subshell and then the 4s. And then after the 4s is filled, you fill the 3d, 4p, and then 5s. And you keep moving along this chart like so. So as the arrow moves from this point to this point, this indicates the order in which you should fill the certain subshells. So if we go to this area right here, so this arrow, you would start by filling the 3D subshell first, then the 4P, and then the 5S. So this is basically indicating to you in which direction you should fill the particular subshells. But if you know the energies, if you know the general orbital diagram, the general energy orbital diagram, you should not need this key. And of course, as you write more and more electron configurations, you will not need to draw this out. And note that this is only a general rule of thumb. There are some exceptions that we will talk about towards the end of our discussion today. So the next rule that we need to know is Hund's rule. And Hund's rule states that when you fill degenerate orbitals, the lowest energy is obtained when the electrons with unpaired spins are maximized, so I'm just going to say maxed, in number. So Hund's rule basically states that when you fill degenerate orbitals, the lowest energy is obtained when the number of unpaired electrons are maximized. So just to give you a little explanation here to show you the difference between unpaired and paired spins. An unpaired spin can be symbolized in one of two ways. So here we have an orbital here, and an unpaired spin is basically when you have only one electron occupying an orbital. So this is symbolized by either a upwards pointing arrow or a downwards pointing arrow in one orbital. So remember that this upwards pointing arrow has a spin of +1/2, and the downwards pointing arrow has a spin of -1/2. Now, a paired spin basically occurs when you have two electrons occupying the same orbital. So you'll have one arrow pointing up and then one arrow pointing down. So you'd have a +1/2 for the upwards pointing arrow and a -1/2 for the downwards pointing arrow. Now, for paired spins, the overall spin number of the particular orbital that is containing these two electrons is 0. However, if you look at the orbitals in this case, the electron in this orbital is unpaired, so the spin in this orbital is +1/2 and the spin is -1/2. So this is the unpaired spin and this is the paired spin. So just to give you an idea of how to use this rule in a orbital diagram, we can do the electron orbital diagram for magnesium. So magnesium has 12 electrons. So therefore, let's use the two rules that we just talked about in order to fill an orbital diagram. So we always start off with the lowest energy orbital, right? And then the lowest energy orbital is the 1s orbital. So before we can move on to any other orbitals of higher energy, we have to fill out the 1s subshell first. So And so we put 2 electrons in the 1s subshell. And note that we are employing the Pauli exclusion principle for this subshell, because remember, you can't have 2 electrons occupying the same orbital with the same magnetic spin quantum number. So they have to have opposite directions in their spin. So one has to be plus 1/2 and the other has to be minus 1/2. So the next orbital that we have, the next subshell that we fill is the 2s subshell. So 2 electrons go in there as well. So that's 4 out of the 12 electrons. So then we move to the 2p subshell. So the 2p subshell. Let's actually separate this a little better so we can see the different orbitals. So here's the 2p subshell. So how would we go about filling the 2p subshell? Well, according to Hund's rule, we have to maximize the number of unpaired electrons. So whenever you fill degenerate subshells, always fill it like so. So you go 1, 2, 3, 4, 5, 6. So always fill it like I just did. So before pairing up electrons in a particular orbital, make sure an electron occupies each of the degenerate orbitals first before pairing specific electrons together. So now that we have our 2p's occupied and we have 2, 4, 6, 8, 10 electrons, we can now fill up our last subshell, which is the highest energy subshell, which is the 3s subshell. And the 3s subshell, in this case, has 2 electrons. And this is our orbital diagram. So now let's convert this to an electron configuration. So an electron configuration is basically telling you how many electrons are in each subshell. So we can convert this orbital diagram to an electron configuration. So we can illustrate this by saying we have 1s2. So this would be our first thing that we would list, and we're saying that we have 2 electrons in the 1s subshell, 2s2, 2p6, 3s2. So that would be our electron configuration for magnesium. So now that I've introduced to you how to make electron configurations and orbital diagrams, I encourage you to do this practice set. So what I want you to do is to basically draw the orbital diagram like we did for magnesium for each of these particular elements, and then convert them into electron configurations. So I encourage you to pause the video and try these for yourself. So hopefully you paused the video and tried these for yourself. So let's go through these together. So let's start off with the first one, which is oxygen. So oxygen has 8 electrons, right? It has 8 electrons. And remember, the way that you can find out how many electrons a particular element has is to look at the atomic number. So oxygen has 8 electrons. So as always, we start off with the 1s subshell because it's the lowest energy subshell, and we put our 2 electrons in there. So then we move on to the next subshell, which is a higher energy than 1s. So this subshell, we put in 2 electrons. And then we move on to the 2p subshell. So we have to follow Hund's rule, so make sure you fill the orbitals in the way that I am filling them. So we go 1, 2, 3, 4. So let's just make sure we have the correct amount of electrons. So 2, 4, 6, 8. So that is our orbital diagram for oxygen. Now we can condense this into our electron configuration. And the electron configuration would be 1s2, 2s2, and then 2p4. And that is your electron configuration for oxygen. So now let's do sodium. Now sodium has an atomic number equal to 11, so therefore we have 11 electrons. So let's fill out our orbital diagram. So we start off with 1s, so 1, 2. Then we move on to 2s, 3, 4. Then we move on to the 2p subshell. So 2p, so 1, 2, 3, 4, 5, 6. And then we put our last electron in the 3s subshell, so 1. And when you condense this into your electron configuration, you will come up with 1s2, 2s2, 2p6, and then 3s1. And that is your electron configuration for sodium. So lastly, let's do calcium. Calcium is a little tricky because we have a 4s orbital in there, but we'll get to that. So calcium has 20 electrons. So let's start off with our 1s. So 1, 2, 2s, 3, 4, and then our 2p. So 2p. So 1, 2, 3, 4, 5, 6. And then we move on to our 3s. So 1, 2. And then we go on to our 3p orbitals. So 1, 2, 3. So this is our 3p subshell. So 1, 2, 3, 4, 5, 6. Now, you have to be careful here. We don't fill the 3d subshell. We fill the 4s subshell next. And remember, that is because the 4s subshell is lower in energy than the 3d subshell. So therefore we fill the 4s subshell before we fill the 3d. So therefore the remaining electrons go into the 4s subshell. So then we can condense this into our electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And that is your electron configuration for calcium. So you may have noticed that some of these electron configurations are very long, calcium being one of them. That was a lot of things we had to write. So we can actually condense electron configurations, and we can shorten them down by writing the closest noble gas element to that particular element that we're writing the electron configuration for. So let's just take calcium. So here's our full electron configuration for calcium. And we can condense calcium by basically eliminating all of these electrons. So all of these let's actually not cross that out. So let's actually put a box around it. So we can basically condense all of these electrons into one elemental symbol. This particular electron configuration in the red box corresponds to one of the noble gases. And that particular noble gas is argon. So argon has an atomic number equal to 18, and it's basically the closest noble gas electron configuration to calcium. So we basically condense this part of the electron configuration of calcium to argon. So we just write argon here, and then 4s2. So this is the condensed electron configuration. So from this we can designate two types of electrons. So the first are the outer shell electrons. So the outer shell electrons are the electrons that are outside of the noble gas configuration. So in this case, in the case of calcium, the electrons within the 4s subshell are the outer shell electrons. So the outer shell electrons are the electrons outside the noble gas core. While the core electrons, let's circle the core electrons. So the core electrons, in this case calcium, would be the electrons within this red box. And the core electrons are the electrons that correspond to the closest noble gas configuration in an electron configuration. So in this case, for calcium, these would be your core electrons, and these core electrons are symbolized by their corresponding noble gas elemental symbol. So that is how you can condense electron configurations. So there's actually a way in which you can help yourself fill out these electron configurations, and that's by identifying the SPD and F blocks. So let's begin with identifying what each of these means. So the first is the S block, and the S block is, I'm going to shade in blue. So the S block will be shaded in blue, and the S block basically consists of your group 1 and group 2 metals. So your alkali earth metals and your alkali metals, and of course hydrogen and helium. So this is your S block. So the S block is your group 1 and group 2 metals, along with hydrogen and helium. So let's label that for you. So this is your S block. So your S block is in blue. And the S block is basically where you fill up your S subshells. So in the S block, the new valence electrons are filling up the S subshell. So let's go on to the P block. So the P block will be colored in pink. This is your P block. So the P block is made up mostly of your non-metals and some metals, but in the P block, the new electrons move into the P subshell. So you're filling your P subshells in this case. So this is the P block. Then this orange region is known as the D block. And the D block is where most of your transition metals will be located. So in the D block, you will be filling your D subshell. So this is the D block. And then the last bit that you should be aware of is the F block. So this is the F block. And the F block is made up of the actinides and lanthanides series. Now, this series of elements has very weird electron configurations. So I don't expect many teachers or many general chemistry classes will be focusing on the electron configurations of these particular species. However, if they do, please look into those. So this is the actinide and lanthanide elements, and this is your F block. So the S and P block elements actually have a special name, and they are referred to as the main group elements. So the main group elements are the S and P block elements. So that's just another name for the S and P block elements. And they're also referred to as the representative elements as well. So that's another name for the S and P block elements. So One of the last things that we're going to be talking about is counting valence electrons. So there's two general rules that you should worry about. And these two general rules are that for main group elements, fully filled D or F subshells are not considered to be valence electrons. So, for example, if you had bromine, bromine has an electron configuration of argon. So it has the noble gas core of argon, and then its outer shell electrons are 4s2, 3d10, and then 4p5. So since bromine is a main group element, you would not count the 3d10 electrons within that subshell as part of the valence electrons. You would only consider the 4s2 and 4p5. So therefore, bromine has 7 valence electrons. And remember, valence electrons are what determine reactivity. So they're the ones involved in bonding and different chemical reactions. So the valence electrons are the important electrons. For transition metals, a fully filled F subshell is not considered to be part of the valence electrons count. So those are the two main rules for valence electrons and counting them. So the last bit of information that you should know for general chemistry is the exceptions. And the common exceptions are chromium and copper. So chromium, if you go through the rules that we talked about above, the expected electron configuration would be what? So I actually encourage you to pause the video and write down what the expected electron configuration would be for chromium and copper. So hopefully you pause the video and use the rules that we talked about above to write the expected electron configuration. So the expected electron configuration of chromium would have an argon noble gas core along with 4s2 and then 3d4. However, this is not the case in reality. In reality, the real life electron configuration is 4s1, 3d5. Now let's do it for copper. So copper also has the noble gas core equal to argon, and you would expect it to be 4s2, 3d9. However, this is not the case. So let's actually cross these out. In real life, it is argon for the noble gas core, 4s1, 3d10. So why? Well, it's actually because, as you could see in our little orbital diagram above, the 4s and 3d subshells are very close in energy. So this allows electrons to sort of jump between those two energy levels pretty easily. And as a general rule of thumb, when there are enough electrons to half fill or fully fill the D subshell, the element will do so. So the electron configuration will reflect that. So here, below here, I have the particular elements that you should be worried about when I'm filling out these electron configurations. So the particular elements that you should be worried about are chromium and molybdenum. Now molybdenum follows the same rules as chromium. So molybdenum would follow the same rules as chromium does. And the electron configuration for molybdenum would be chromium, no, not chromium, it would be krypton for the noble gas core, 5s1, and then 4d5. So that would be your molybdenum electron configuration. Now, copper, silver, and gold follow the same rules as copper. So let's just do silver, for example. So silver would have the core electrons associated with krypton, and then krypton, and then you would have your 5s1 and then 4d10. And that would be silver. And then gold follows the same sort of rules, except you have F subshell being filled. So these, let's actually write it out for gold as well. So gold would have the electron configuration associated with a noble gas core of xenon, along with 6s1, 4f10, 4f14, and then 5d10. So this would be the electron configuration for gold as well. So as you can see here, they're following the same rules as copper, and molybdenum is following the same rules as chromium. So you don't have to memorize all of these if you know the rules for chromium and copper. So that concludes our talk for today. So here I just have 2 practice questions for you to try on your own. So what I want you to do is I encourage you to pause the video and try these questions for yourself. Okay, so hopefully you paused the video and tried these questions for yourself. So let's go over these together. So write the condensed electron configurations for the following elements. So the first is strontium. Strontium has a noble gas core of krypton, and the outer shell electrons fill the 5s2 the 5s subshell. So this would be the electron configuration for strontium. So manganese, for manganese, you would have the argon noble gas core, along with 4s2, and then 3d5. And then for sulfur, the sulfur electron configuration would have the neon noble gas core, along with 3s2, and then 3p4. And then silver, you have to be careful with silver because silver is one of the exceptions that follows the rules of copper. So it would have the electron configuration with a krypton noble gas core with 5s1 and then 4d10. So those are the particular electron configurations. So the next one is a multiple choice. So which of the following electron configurations for a ground state atom is allowed or are allowed? And you can choose multiple answers. So this is just making sure that you understand the particular rules. So the first one says that we have a helium noble gas core along with 1s2 and 2s1 outer shell electrons. However, what's wrong with this choice? What is the configuration for helium? The configuration for helium is 1s2. So therefore, if we're saying we have, you can transfer this as 1s2, 1s2, 2s1. And if you simplify this, you're saying that there are 4 electrons in the 1s subshell and then 1 electron in the 2s subshell. So obviously this is wrong because you can only have 2 electrons in a particular orbital. So the next is has a xenon noble gas core with 1 electron in the 6s subshell, 14 in the 4f, and then 10 in the 5d subshell. And this, in fact, is actually a possible electron configuration. And that's because this is the electron configuration of gold. So this is for gold. So this is perfectly fine. It obeys all our rules, and it's one of the exceptions. So therefore, this is possible. So next states that we have a noble gas core associated with krypton, and then outer shell electrons in the 5s, 4d, and 5p subshells. So you'll notice here that we're following all the rules. There's enough. Each orbital is occupied by no more than 2 electrons. And if you look at the periodic table, this particular electron configuration corresponds to the element of iodine. So this is actually iodine. And that is a correct answer as well. So the last one is D, and it states that we have an electron configuration of 1s2, 2s2, 2p4, and 3s2. Now note that this is not a ground state atom, because in order to have the lowest energy atom, you have to fill lower energy orbitals first, and then you can fill higher energy orbitals. So this is wrong in this case. However, if you absorb enough energy and you're in an excited state, you can maybe have something like this. So this is not right for a ground state atom. So with that, that is all the practice questions for today, and this concludes our lecture for today. I thank you all for watching, and if you have any questions, please ask them in the comments section. And in the next video, we're actually going to start applying what we learned about atomic structure to the behavior of particular elements. So we're going to be talking about the periodic properties of the elements. So we're going to be talking about ionization energy, effective nuclear charge, electron affinity, electronegativity, all that stuff. So we're actually going to understand how particular elements behave. So thank you all for watching, and I hope to see you next time. Good luck, everyone.